Welcome back to BAS 120. We're going to talk about binomial distribution, problems 5.23 and 5.25. Now, I've got linked some optional, very good video series that go into in depth on the binomial theory, which if you need some help, you've got lots of help. I've put it optional. So binomial distribution is where I have events that are either success or failure. So, for example, in this example, a foul shooter. I either make the foul shot or I miss the foul shot. I flip a coin or I don't. My product passes inspection. It doesn't pass inspection. So let's say John is a 70% foul shooter and his team trails by 1 point. There's no time left at the clock, and John's going to shoot 2 foul shots. What is the probability that his team wins in regulation? Now, I don't want to get into he makes one, it's tied, it goes into overtime, all that. They got to win in regulation. So I got 4 outcomes. John could failure. He could miss them both. He could be successful on the first and then fail on the second. He could fail on the first, success on the second, or he could have success and success. Make them both, basically. Now, that's the only one that wins the game. They're behind by a point. They need 2 points. There's 4 outcomes. Only one of them wins the game in regulation. So, our X in this case is 2 because he has to make 2 foul shots, and our N is 2 because he has 2 trials. So we go to, I went here and I said, here are the number of successes. He can either make 0 foul shots, 1 foul shots, 2 foul shots. You can go to this, since we have a binomial distribution, Excel has a binomial distribution. First thing you put in is how many successes are we assuming? Second thing you put in is what is the probability of any given event? They tell us he's a 70% foul shooter, so we say 0.7. Let me open this up so you see it. There. And Excel always gives this to you, right? S is the number of successful trials. Well, I've made this a cell so we could fill this down. How many trials are we doing? Well, he's got 2 foul shots. That's it. What's the probability he makes any 1 foul shot? Is 0.7. Now this last one says, do I want it to be cumulative or do I not want it to be cumulative? So the first thing I did is I said, let's say false in here, and that'll give us the probability that he makes exactly 0 or exactly 1 or exactly 2. So the probability that he misses them both, thanks to our team, is only 9%. So most likely it's either going to overtime or we're going to win the game. The probability that he makes 1, exactly 1, is 42%, 0.42. And the probability that he makes 2 is 0.49. So the probability that we win the game in regulation is 0.49, 49%. Now over here is the binomial distribution. Only what we've done here, all the same data, only notice down here the cumulative, we said make that true. Make it be cumulative. So now we have a cumulative distribution. Well, not surprisingly, the 0 is still 0.93. The probability if he makes 1 or less is 0.51, which is the addition of this 0.49 and 0.42 in this 0.09. And of course, the cumulative probability that he makes 2 or less shouldn't shock us, right? The probability that he makes at least 2 or less is 100%, because he can only make 0, 1, or 2. So be familiar with, if I've got a binomial distribution, which again, review, that's where we have events that are success or failure. We have a defined certain number of events. We meet all these criteria. Yes, John either makes or misses a foul shot. Yes, John has exactly 2. And we know the probability of any certain event. We know he's a 70% foul shooter. We can use the binomial distribution. False criteria. False means we don't want it to be cumulative, so that'll give us the probability of getting this specific event. He makes 1, 42%. If we say true to that cumulative, that'll give us what is the probability of he makes 1 or fewer. Accumulates it for us. All right, let's try another one. Let's say John claims to be an 85% foul shooter. You go to the gym with John, he takes 30 foul shots. He only makes 20. That's 67%. According to John, he had an off day. I had a terrible day. It rarely ever happens. Well, let's think about this. Do we want to believe he had an off day, or do we want to believe he's inflates his capabilities a little bit? Well, we meet the criteria of a binomial distribution. So let's just see. Here's success, and I've started with 20 where he had. I put binomial distribution false. So the probability that he makes exactly 20 is very, very low. But what we're really interested in here is the probability that he makes 20 or fewer, right? So over here I said on that particular day he shot 67%. But there's about a 1% chance that if John is truly an 85% foul shooter, he's going to go out there and only make 20. So, now it becomes a subjective, a little bit of a subjective nature. Do you want to believe John and see take a few more trips to the gym? Or do you want to say, gee, there's only a 1% chance you had that bad an off day. I really don't believe you. And that's going to get into future chapters when we talk about hypothesis testing. But I just want to get you to start thinking about it. Now, notice what's happening in here. We can do some summations and say, the probability that he makes somewhere between 24 and 28, we could have either just added up the individuals, or we could have taken the 95 minus the 15, right? The cumulative probability that he makes 28 or less minus the cumulative probability that he makes 23 or less, because remember we said equals to 24. So about an 80% chance. So 80% of the time when we go to the gym, we would expect him to make somewhere between 24 and 28%, if he's truly an 85% foul shooter. So this is where the power of the probability distribution function, and regardless what distribution, we're going to see it can be several different, there's lots of distribution functions. Binomial distribution isn't the only one. In fact, we're going to show you some more in a minute. In fact, let's get into a different one. But this is where the power begins to come in. Let's talk about a Poisson distribution, okay? Again, there's a lot more optional videos that go through the Poisson distribution in detail, but let's say a Poisson distribution is where we have an event where, it's a timing, like people arriving at a subway. And we know that on average, 12 per hour arrive at the subway. Well, what is the probability that only 5 arrive, or that 15 arrive, or that 23 arrive? Well, this false and true for the cumulative is going to come in the same way. We're going to do the same thing, except now we're going to use a Poisson distribution. And we're going to say, what's the probability of this value? In this case is 5. I know the mean is 12 because they've told us the average it comes in. And I've said false because I want to know the exact probability that 5 will come in. The exact probability of 5, as you might expect, the exact probability of any one number tends to be fairly small. Here is the cumulative probability. So the probability that 15 or fewer is 84%. The probability that 23 or fewer is 99.9%. The probability of 5 or fewer is only 2%. Now, think of the power of this if I've got, thousands of Subway stores and have to do staffing. I save 5-10% on staffing. It helps tremendously. Staffing levels, suppose I don't want to equate waiting for a Subway to a delivery at a hospital. Certainly you'd want to build in more buffer or safe buffer. Like Subway, I might be willing to live with coverage of 84% of the time somebody doesn't have to wait more than a certain amount of time. Certainly if I'm talking of deliveries of babies, I might want to make sure that I'm coverage is much higher, right? Because I certainly don't want people to be waiting for delivery of that. But you could do the same thing. Suppose the babies are born during an 8-hour shift at a hospital, follows a Poisson distribution with a mean of 6. Find the probability that 5 babies are born during the 1-hour period. Very simply, told us 5 or fewer. Mean is 6. We said false because they asked us exactly 5. Probability of exactly 5 is 16%. If we wanted to know 5 or fewer, we would just simply take this and say true instead of false. So I could copy it, paste, and just say true. Now, the cumulative probability, hopefully your catch, is going to be higher than the probability of exactly 5. And then we get about 44% of the time. And that makes sense because the average is 6 arrive. So 5 arrives just about halfway there. So that makes a lot of sense. 5 or fewer, 44% cumulative probability distribution. Hope that helps. One last topic before we go is uniform probability, and this is very, very rare that we have this. But if we know that the probability is uniform, the same throughout the curve, then we could very simply say the probability, and we know it's between 1,000 and 2,000. We could say the probability of less than 1,300 is equal to 1,300 minus 1,000 divided by my entire range. Because what I'm basically doing is saying, well, how much of this range of this uniform distribution have I covered? Well, I've covered 30% of it. So the probability is 30% of that event. These are very rare that you get a uniform probability distribution. Normally it's some other function that you come up with, which let's talk, since we're doing it, 5.29, the normal distribution, okay? Now the normal distribution has a mean, talked about mu, and a standard deviation symbol there where we sum up all our differences from the mean, square them just like we did the variances, divide by n, and then take the square root of all of this. Here's a distribution of the normal curve. Most folks are familiar with it, and it's very interesting. Notice here, mu minus 1 standard deviation is plus or minus 1 standard deviation, combines both of these, about 68% of our population. 2 standard deviations, if you add up the 13, the 34, that's about 95%. And 3 standard deviations is about 99.7. Now, just to keep me honest, I happen to notice there you see them all. And a z-score is nothing more than it standardizes it by taking our x minus our average, dividing by the standard deviation. So notice 1 standard deviation is a z-score to the left is a z-score of -1. 1 standard deviation to the right is a z-score of 1, etc. So a z-score is just a standardization on the normal curve by taking whatever value we have, comparing it or subtracting it from the mean. How far away from the mean are we? And then we're standardizing it by dividing that difference by the standard deviation, which gives us a z-score, which basically tells us how many standard deviations to the left or to the right are we from the mean. We'll do some examples and show you. Well, let's do an example. What is the probability that demand will be at most 90 units, at most 900 units? Let's do 900. Let's not do 90. 900 units. If we know the mean is 750 and the standard deviation is 100. Okay, so we can do at most. So that's 900 or less. Okay. Now, since we've got a normal distribution, we'll use the norm dist within Excel. And you need to learn these tools: norm dist for normal distribution, Poisson for Poisson distribution, binomial for binomial distribution. They tell us our x is 900. They tell us the mean is 750. They tell us the standard deviation is 100. And because I want to know at most 900 or left, I want that cumulative from 9. I want it to be cumulative probability all the way up to 900. So the probability of I get 900 or less is 93% or 0.93. which makes sense. We're very high. We're very far to the right of our mean. Now, what about more than 700? Now, notice what I'm doing here. More than 700. Remember, our cumulative distribution function gives us from left to right. So if I say norm disk up to 700, that'll tell me all the area to the left of 700. But my question is, what is more than 700? Well, again, if I take 1 minus how much is less than 700, I'll have how much is more than 700, which is right there, 69%. And again, that makes sense. If the mean is 750, 700 and more has to be more than 50%. So it's about 69%. Now, how much is between 700 and 900? Well, I can say, what is my curve? What is my area from left to right up until 900? That'll give me the probability of it's 900 or less. And then I subtract from that the probability that it's less than 700. And that'll give me that it's between 700 and 900. And that's about 62%, which that always makes. You should always check to make sure these make some intuitive sense. If my mean is 750, then yeah, between 700 and 900 is going to be around 62%. Hope this helps. There's more examples, and there's a lot more homework examples where we'll be doing all of this, working with these different distributions.